Hello everyone, my name is Christopher Dankosik. In this video we'll be going over a prototype electronic control unit board for Global Motorsports 2023's design and going over all the features, going through a little bit of testing, and showing the overall functionality and improvement of the board for the newest rendition for the 2024 team to possibly use. Not much has changed in terms of the fundamental circuit design of the board. What it has changed is that it is in a much more miniaturized format, combining our previous BSPD and PCM year's boards from 2023 together to a much more miniaturized format. Um, there's been some added features for integration of signal testing and such, so you simply just have to flip some switches on the board and just some potentiometers to test the signals that you want. So you can do that on the car and make sure everything's working, and then actually plug in things you actually want. It has 3 digital inputs and digital outputs that will be utilized through a microcontroller that you can do for testing as well, and interact with the motor controller. And additionally, to cut down on space from usually having an external fuse box, I decided to put the fuses directly on the board through some panel mount fuse holders. So let's go ahead and take a look at all of this. Starting with combining the two boards together, on the top we have our previous year's BSPD. So that handles all of the signals for the brake lines pretty much. So pretty much brake signal comes in, that also gives a signal to the hard brake. And this is what had our signal to the shutdown circuit last year. So combining all this onto one board along with the PCM, we basically just have one shutdown circuit on one board, along with all the other motor controller signals as well that would usually come into it and such. And also, some other added features to the board is that I decided to add in some, instead of having a big amp seal connector, we simply just have screw terminals where you can put in all the different wires and such, generally just making it a lot easier for the wire management. And all of this can just simply be put inside of an enclosure, then to protect it from weather sealing and all of that stuff. In terms of the layout of the board, everything is laid out into little modular units. So, for example, the whole entire sheet for the brake side, that is simply put inside its own little box, if you would, along with all the other ICs, potentiometers that go with it. So it's going to be very easy to diagnose and know what values and potentiometers go to what to adjust signals and such. Same with the motor block as well. That's all in its own one. Shutdown circuit is laid off separately as well. APPS and all the digital I/O and such, along with the test circuit and such, has all been laid out. And additionally, note that the green screw terminals are all marked as well. So starting off, we have 3 main signals coming through the board: our brake light OK, which is first when we turned on, and our motor current high and motor current low. So the 2 green LEDs are indicating the status of the brake OK and the motor current OK. And we have potentiometers on those voltage dividers, which the signal comes from, that we can adjust on the board. So right now I'm turning the potentiometer for the brake light OK. So now we're going to drop that signal low enough so we can turn off the brake light OK. And all these threshold values can be set by the appropriate other potentiometers on the board, which will come for your doing your own testing on the car and such. And so now once we drop that voltage low enough from the brake signal, we can turn on that LED high and low. And also notice the LED that we have on the top there coming from one of the green terminal is our brake light at the moment. And so notice that it is still on while we have the brake light OK off, and we're messing with that. And so this all has to do with just adjusting the threshold and such. So right now, let's go ahead and adjust the threshold for the brake light, as we can additionally turn that light off while having the brake light OK on. So let's go ahead and turn that potentiometer. All right, turned it off. So now we have set that threshold so it's low enough at the given voltage that we have. And really, you're going to know what those voltages are when it comes to doing your own testing on the car. So just know you have a lot of leeway to mess with things for turning on the signals. So now let's go ahead and turn off the brake lights and the motor current high and the motor current low. As for the IOs added to the board, we got 3 discrete inputs and 3 discrete outputs. Starting from the left-hand side, those are going to be discrete inputs. They're all appropriately marked next to their green screw terminal as well. So all you simply have to do is hook up the signal to terminal 1 on the board, which is marked, and then it goes to 2, then to a voltage divider, and then from there you can read in the signals such. So these are most likely going to be used for reading in signals from the motor controller. When say like signal goes high, gives out 12 volts, you're going to be able to read that, or any other use you have. As for the discrete outputs, it's basically just it gets a 3.3 signal that goes through that 1K resistor that then goes to the base of an N-channel MOSFET. So for hooking it up, at least you would have to put in the device on screw terminal 1, and then to ground, which is on the second side of the screw terminal, which is marked on the board. And then once you turn it on, you get 12 volts to ground across your whatever it may be, from like you say, the radiator, fan, or pump. Then turning it on with the PC, or the PC in this case. As for the integrated fuses on the board, it's pretty straightforward. You have one side that's connected to 12 volts. That then goes to the fuse. Then through whatever side of the terminal you put your connector on, or your input to the device on, and then to ground. And with this being a prototype board, I did run into some fixes and troubleshooting that I had to do. The first one was fixing some floating logic that I had because it didn't have a ground reference from the potentiometers that are coming from the test circuits. So that was a relatively easy fix. I simply just had to add a grounding resistor so the logic would no longer be floating and be defined whenever using the test signals. I did run into a couple of small layout mistakes. That was just mostly due to my side. This board was designed in about under a week, so that's just because I had to really fast track this to get this in time to 2023 teams start testing. So, but they weren't too bad. Only about 3 mistakes, so those are pretty easy to fix and address. And then additionally, I was trying a more reliable way for shutdown circuit to implement it, such as on the BSPD, we did not test it and had no idea if it worked. So I at least wanted to give it a shot, trying to get something working. And unfortunately, I was able to get it halfway working, but not reliable enough for I think to utilize in the car. So that's going to have to be better implemented in the next upcoming iteration and such, if this board is going to be followed by 2024's team. So to start off, addressing the floating ground issue. You see on the left-hand side, we have 3 voltage dividers. So these voltage dividers, 5 volts comes in, goes through the potentiometer, which adjusts the voltage of the test signal. And then that goes through a dip switch, which will then connect it to that part of the circuit that it needs to go through. So, for example, if we take a look at the brake line signal, 5 volts comes from the top, goes through a potentiometer, that resistor to ground, but we're taking the output from the potentiometer, and once we turn on the dip switch, it goes to where typically the brake signal will go if we hooked it up. The issue was, though, it was that wiper of the potentiometer doesn't have any reference to ground. So basically what was happening was hooking it up, the logic was floating, so sometimes it would turn on, sometimes it would turn off. So this was a simple fix just by adding a grounding resistor. So I added a 1 mega ohm resistor across each of the signals. So it could be properly grounded, so when I turn on the dip switch, that signal will be properly grounded and referenced to the op amp. As for some of the layout mistakes, there was a mistake for the 5 kilowatt signal. one for the break OK, another for that chip being grounded, and then additionally you see there we have the 1 mega ohm resistor that we previously talked about for fixing the floating ground issue. So first off, if we go ahead and look at the layout for the 5 kilowatt signal that then goes to our NAND gates, which implements the logic shutdown circuit, it just simply wasn't connected to um, that NAND chip. So basically, I just took a wire you saw previously and just soldered it to where it needed to go. Just for the break OK signal, it was the same case. So if we look at the black line there, it just simply from the AND chip did not go to this chip over here that we have for the shutdown circuit. And additionally, there was a ground problem too as well for the AND chip. So if you look at where the ground is connected to, it's almost on like its own little island, if you would, not connected to the grounds of the rest of the board. And that's a kind of issue you can run in sometimes with the nets that we have on the board. It would connect to something called ground, but that ground isn't connected to the rest of the grounds. So I simply just had to add a wire just connecting it to the main ground of the board. Also, having copied most of the circuitry from the 2023 design, actually I discovered a mistake in it for the logic of the shutdown circuit. So the way that we have the shutdown circuit working is that if we get either the errors from the 5 kilowatt signal or the hard brake, it should shut down the car. But at the moment, both of these errors need to happen in order for the car to be able to shut down, which really doesn't make sense. If you get an error, you want that thing to be able to shut down the car. So if we say, for example, the 5 kilowatt, which comes from the current sensor and such, trips, but we still have the hard brake reading us perfectly fine, it's not going to be able to shut down the car. Looking at the Boolean logic for it real quick, for a NAND chip, you see that for 0, 0, it's going to be outputting a 1. And so for the error signals, those are usually going to be normally low. So our NAND chip, excuse me, is going to be outputting a 1, which then goes to the next one that we see, U16. Breaks OK and the current sensor OK are usually 1s. So then all of those 1s output a 0, which then goes to a P-type MOSFET, turning it on. So then now you see the issue here. So if the 5 kilowatt signal, say, goes high, let's call that A, you have 1, 0, but it's still outputting a 1. So now it's not able to turn on the shutdown circuits. And so thus the fix I made for that is simply just tying these signals all together and such. In my case, I used a 3 NAND device just so I can cut down on having to use 2 different chips and such. I just used one that had 3 and just had to basically just tie the signals together for what I needed to get the logic copied from 23. But just to note, this is going to have to be a temporary fix and something that will be further addressed for 2024's team. As for implementing a new way for the shutdown circuit on the board, for the BSPD, ours was not tested at all and not verified, so I quite honestly had no idea if it was working. So I came up with my own solution just to try and put some ideas forward and such. So the way it works is that 0 volts will be coming down from the NAND chip, which is going to be normally functioning in terms of the status of the car. And then that goes through a RC network. So 0 volts going for RC network, that's just going to be 0, and then that additionally goes to a P-channel MOSFET. And so when you have a 0 on a P-channel MOSFET, that basically acts as an open or a closed switch, excuse me. So that's going to be allowing 12 volts to go through, in this case, it's going to be going, let's type up P-channel real quick. Okay, there we go. So then 12 volts is going to be going to one of the coils of the relays that we have here, turning it on. So then that closes the relay, and then that 12 volts is allowed to flow through this coil going up to here, but this coil is not turned on. So let's look at it again. So 12 volts goes through that coil, goes through the coil that will be for the shutdown coil, and then up to there. But it doesn't have a path to ground yet. So the one for the shutdown coil, it doesn't latch yet. That coil is just a floating 12 volts. And this is where we have a start button. So when we press the start button, we energize the coil that goes to ground, which will close that latch, and then that other coil finally has a path to ground. And so let's take a look at a simulation of it real quick, showing how this would work. So looking at a simulation, this is the way the car would look when it's normally running and such. So we have a 0 going to the P channel and then allowing current to run through everything else once we have pushed the start button. And so then once we get a fault, you see as we trigger the P channel, now sending 12 volts to the RC network, allowing it to slowly charge to basically the P channel. And then once we clear the faults, we allow current to flow through again to the car, closing the relay for the shutdown coil. And looking on the physical layout of the board as well, we see we have two green terminals, one for the start button, where you hook up the start button as we had the previous diagram, to turn on one of the relays. But the latching effect, since we were running into problems with the previous RC circuit and such, isn't working at the moment. So what you can do is just manually shut down the shutdown circuit through just putting a button to the coil for the shutdown circuit, doing your testing like that, and then just measuring to see when you actually get a fault and such to do your preliminary testing.